Today we will discussing high rate pulverized coal injection in blast furnaces. This presentation is a theoretical consideration of the key problems and advanced solutions associated with technology, focusing on the practical experience and success of Bao Steel in China. Since the late 1990s, Bao Steel has successfully sustained coal injection rate over 200 kilograms per ton of hot metal, providing invaluable insight into the operational limits and requirements of modern blast furnace iron making. Our goal today is to understand the critical factor that enable such high performance and measures that can taken to increase coal injection rates. Pulverized coal injection (PCI) is a cornerstone of modern iron making. Its primary purpose is to reduce blast furnace dependency on high quality expensive coke by replacing up to 50% of the coke with more readily available pulverized coal. The PCI techniques significantly lessen the reliance on the coke making process. These technologies are rapid development starting in 1980s, largely driven by economic factors like soaring fuel prices. Today its importance is amplified by the growing demand for environmental protection and a global shortage of coking coal. As a result, PCI improved the overall competitiveness of the blast furnace process, which remained the most efficient, lowest in energy consumption, and highest in the production for making quality pig iron. The success of high rate PCI is exemplified by Steel, which since 1999 has maintained an average coal injection rate as high as 207 kg per ton hot metal. One of their furnace even achieved a record monthly average of 260 kg per ton hot metal, demonstrating the remarkable potential of this technology when optimized correctly. However, injecting coal at such high rates introduces significant operational challenges, with the most critical being the impact on furnace permeability. Poor permeability can lead to a phenomenon known as flooding, where the high upward flow of gas prevents the downward movement of the liquid slag and metal. This can cause the furnace to hang and disrupt production. High rate PCI worsen this problem in several ways. First, unburned coal generate a high amount of dust and fine particle. Second, using high volatile coal increases the specific volume of gases in the tear zone. And third, the accumulation of these unburned particle can decrease the empty space or void fraction in the coke bed and increase the viscosity of slag, making it thicker and harder to drain. While there is some debate whether flooding or fluidization is the ultimate limiting factor, the practical outcome is same. Poor permeability restricts how much coal can be injected and limits overall furnace productivity. This is why high quality raw material are essential to counteract these negative effects and maintain a stable operation. So, why did Bao Steel succeed in sustaining PCI rate over 200 kg per ton hot metal when previous industrial experiments failed? The sources point to one clear answer: the superior quality of their raw material. If we compare the input at Bao Steel with those at Bauto and Ansen, where earlier tests did not meet their goal, the difference are stark. As you can see in the table, Bao Steel used sinter with a much higher iron content, 58.5%, which leads to lower slag volume and better permeability. Even more critically, their coke quality measures by coke strength after reaction, or CSR, was significantly higher at 69.54%. High quality coke maintains its integrity inside the furnace, ensuring the coke bed remains permeable. The conclusion from this is clear: high quality raw material, particularly high iron content ores and high strength coke, are the most essential factor in determining the achievable level of PCI rate in a blast furnace. Coming to our next slide, which is about the managing the thermal state of the furnace, is another key challenge. When injecting coal, you need to add extra heat, and operators traditionally rely on a calculated value called theoretical flame temperature, or TFT, to guide this. However, at high PCI rates, conventional methods for calculating TFT were found to be unsuitable. At Baosteel, these older models suggested the furnaces were running colder than they actually were, implying a need for more heat than was being used for their smooth operation. This led to a development of a new, more accurate method for calculating flame temperature. This proposed model is better for three reasons. First, it adds the sensible heat from the pulverized coal itself. Second, it calculates the heat from the blast moisture based on correct water gas reaction. Third, most importantly, it takes into account the incomplete combustion of coal in the raceway by introducing a coal combustion efficiency factor. The impact is significant. The new method calculates much higher flame temperature, in some cases more than the optimum higher, which align with the real world performance at Baosteel and confirm that their furnaces are operating within the desired thermal range. Now, since coal combustion efficiency is a cornerstone of the new model, it's important to understand what influences it. The sources show that several factors have a major impact. The most significant is the VM in coal. High VM coal has a combustion efficiency more than double than that of low VM coal under the same condition. Blast temperature is another critical factor. As the temperature increases, combustion efficiency rises dramatically. Conversely, an increase in blast humidity actually decreases combustion efficiency. The coal injection rate itself has a strong influence. As the injection rate goes up, combustion efficiency goes down considerably. Finally, and perhaps surprisingly, the data shows that oxygen enrichment has a very limited effect on improving coal combustion efficiency. With this understanding, we can see that blast temperature and oxygen enrichment uh, plays two very distinct and important roles in high rate PCI operation. The primary and the most cost effective method for heat compensation is a high blast temperature. It provides the necessary thermal energy to balance the cooling effect of injected coal. Oxygen enrichment on the other hand should be viewed mainly as a gas flow control tool. Its main benefit is not raising the temperature but reducing the volume of gas in the furnace wash. This helps prevent flooding, which in turn allows for higher furnace productivity. In China, the cost for a 100-degree blast temperature increase is only about half that of 1% increase in oxygen enrichment, making it the preferred method for heat. The experience at Boystill suggests that an oxygen enrichment of 1.5 to 2% is reasonable for PCI rates over 200 kg per ton hot metal, especially when blast temperatures are already above 1200 degrees centigrade. So, in conclusion, we can draw several key takeaways for achieving high rate coal injection. First, high quality material are non negotiable. High iron content in ores and high post reaction strength coke are fundamental for ensuring good furnace permeability and productivity. Second, an accurate calculation of theoretical flame temperature is crucial. The new model, which incorporate coal combustion efficiency, provide a much more realistic view of the furnace thermal state, confirming that high PCI rate are manageable. Third, it's essential to use operational levers correctly. High blast temperature is for heat compensation, while oxygen enrichment is for managing gas flow to maximize productivity. Finally, the sources purpose a theoretical upper limit for coal injection based on the complete combustion of unburned coal within the furnace. This limit is estimated to be around 290 kg per ton hot metal under Baosteel's condition. With record rate already reaching 260 kg per ton hot metal, we are approaching the practical and theoretical maximum of this technology.